Now we are going to draw the half adder by using only NAND gates and NOR gates. We know how our half adder works. So let me draw the block diagram. We know there is HA. HA takes exactly two inputs, A and B, and it gives out two outputs, S and A. And we know S is equals to A, not S and A, it will be S and C. S is equals to A XOR B, which can be given as A B bar plus A bar B, or in max terms, it will be A plus B into A bar plus B bar. Or we can go for C, which is AB, and that's it. So let's start drawing with only NAND gates. We know S is equals to AB bar plus A bar B, and we have to take the minterms Y, then only we can rearrange it for NAND gates. So it will be A B bar into A bar B. Here we will have a whole thing bar, here we will have a whole thing bar, and then we will cover everything with another whole thing bar. And C is just AND gate, so we will need two NAND gates. Now let me tell you how many gates we will need. Here we will need one NAND gate, here one, and then we will need one here, and then finally everything will be put through another NAND gate. So we will need 5 here, and here we will need 2 NAND gates. Alright. Now, since there are no signals in S that can be reused for C, there will be totally 7 NAND gates required for creating a half adder. But in industry, they don't use 7 gates, they use 5 gates. That's where optimization comes in. Okay, so let's start drawing that. We will have A, we will have B, and let's draw the A line and then the B line. First of all, what they do is they send A and B through a single NAND gate first. Okay, that's what they do. So we will get A dot B whole thing bar. This is going to be used multiple times. So let's draw a line for that also. First of all, we can get C easily, right? We'll get A dot B and then send it twice through a single NAND gate. And we will get A dot B, so which is C. Okay, that's it. Now, what they do is they send A and A dot B whole thing bar through a NAND gate. That's what they do first. Then they send B and A dot B whole thing bar through another NAND gate. Finally, they send these two through a NAND gate. And this results in actually S. How does that work? Well, that's why I'm here. I'm going to explain you how it works. First of all, let's come up with the expression that we derive. So here we have A. So, and here it's at A dot B whole thing bar. So we will get A dot B whole thing bar. And here we have B. And since the other part is A dot B whole thing bar, we will get B dot A dot B whole thing bar. And the final term will be equals to, instead of saying S, we'll call it as X. So X will be equals to A dot B whole thing bar into B dot A dot B whole thing bar. Now we are going to simplify this using Boolean algebra. First of all, let's apply De Morgan's law, and we will get A dot B whole thing bar double bar plus B dot A dot B whole thing bar. According to double complementary rule, this double bar and this double bar will be cancelled out. So we will only have A dot B whole thing bar plus B dot A dot B whole thing bar. Now I can simplify this into A dot B whole thing bar into A plus B. Okay, and we know A dot B whole thing bar is actually A bar plus B bar into A plus B. And the thing is, this is the max terms version, max terms Boolean expression for an XOR gate. So X is equals to A bar dot B bar into A plus B, which is also equals to S. That's how we only require 5 NAND gates to come up with the half adder. Now let's go for NOR gates. Okay, NOR gates is actually pretty simple. the simplification is very straightforward. First of all, let's write the max term equation, which is a plus b into a bar plus b bar. Okay, now we can rearrange this for NOR gates only. So we will get a plus b whole thing bar plus a bar plus b bar whole thing bar whole thing bar. That's it. Okay, now the interesting part is, okay, if you take a closer look, here we will need one NOR gate. Here you will need one NOR gate. Here you will need one NOR gate. And for the whole thing, you will need one NOR gate. And then finally, to send them through another NOR gate, you will need 5 NOR gates. That's only for S. Then how many we will need for C? Well, C is A dot B. Okay, A dot B. Which means it will require 3 NOR gates. Okay, 3 NOR gates. Why? It will be equals to A bar plus B bar whole thing bar. This is equals to A dot B. But the beautiful thing is, this is already created by using 3 NOR gates here itself. So we will be reusing this to come up with the output carry. Okay, so that's it. So you know the idea. It's very simple. So let's draw the diagram. We have A and B. We'll draw the A input line and then B input line. First of all, let's get done with the A bar and B bar. So we'll send A twice through a NOR gate. Then we'll send B twice through a NOR gate. And we will have A bar and B bar. Then we will send these two through a NOR gate to get A bar plus B bar whole thing bar. A bar plus B bar whole thing bar. Then we will send A and B through a NOR gate to get A plus B whole thing bar. This will give me A plus B whole thing bar. And this will be C. And if I send these two through another NOR gate, that will be S. Now if you look at it, we only required 5 NOR gates to come up with the half adder. So that's it. That's the topic of the video and it is done. In the next video, I will be coming up with full adder. If you found this video on how to draw half adders by using only NAND gates and NOR gates helpful, don't forget to like, share and subscribe for more lessons. I'll meet you in another video. Until then, keep learning and stay curious. Bye bye.